Okay. Welcome, everyone. Thank you for attending today's online event, Introduction to Population PKPD Analysis using Phoenix NLME. If you experience technical difficulties joining the WebEx session, please dial 1-866-229-3239 if you're located in the United States or Canada. For all other countries, please dial 1-408-435-7088. To eliminate background noise, all phone lines will be muted for the duration of the event. Welcome, and my name is Suzanne Minton. I'm a marketing specialist at Certara. Next slide, please. Please feel free to ask questions at any time during the event by clicking on the question mark icon on the floating toolbar located at the top of the screen. Please be sure to address your question to the default selection in the Q&A so that it goes to all panelists. We will address as many questions as possible during the Q&A session following today's presentation. This event will be recorded. A link to a replay of today's webinar will be emailed within the next few days. Before we begin today's presentation, I would like to introduce the speaker, Dr. Serge Guzzi. Serge has over 23 years of experience in the field of modeling and simulation. He is currently a full professor of pharmacometrics at the University of Maryland, president and CEO of Pop Pharm, and a senior consultant at Certara. Serge is the co-developer of the MC-PEM algorithm for nonlinear mixed effect modeling. He earned a bachelor's degree in chemical engineering in Belgium, followed by a master's degree in chemistry at the Weizmann Institute, and finally a PhD at the Technion Institute of Technology in biomedical engineering. Serge completed a postdoc at UC Berkeley in chemical engineering and then conducted research at UCSF for 6 years. He founded Pop Pharm, a consulting company that has had a strategic agreement with Certara since 2011. Currently, Serge is involved heavily in both the development of NLME as well as training in both the United States and Europe. I'll now turn it over to Serge to begin today's presentation.
Thank you, Suzanne. Welcome to everybody. Here's what we are going to do today. We don't have too much time. Then I assume that the people, the audience, has some background in population PKPD, but not too much. You were not too much exposed to the software, to the NLME software and the Phoenix environment. Then the goal in this presentation is I'm going to give you a simple example of PKPD, and not only to show you how to use the software, but also to give you some information about how to do optimal model building, because I think that's something that is very important. And what you are going to see is that the way the software has been designed in such a way that it's very easy to really run a full optimal model building strategy, and at the end, hopefully getting the results that you need. Now, there are different steps. The first step is that you get data. Then you need to know how to import data, and you need often you need to manipulate the data set because the data set is not given in the format that it's an NLME format. Most of the time you're going to get data either from a non-mem data set or a monolith data set. Then you need to do something. There's a full set of manipulation tools that are available within the Phoenix environment, and I'm going to just to show you how to do that. I'm not going to run any model here because we don't have time, but I already did it in advance. I'm just to show you the process. Then you say, okay, then we have now the data in the right format. Then what's the next step? Within the Phoenix software, you have also non-compartment analysis that can be very useful to be used in conjunction, in combination with population analysis. For example, you need to get some information about clearance and volume. Now, you get information about clearance and volume, and you want to use that once you are going to start your population PK analysis. Then we start on the population analysis. And you need to create a model, which is called a Phoenix model object. And then you have to start to test, okay, 1 compartment, 2 compartment, check what is better, 2 or 1 statistically, and also then run the model, and then look at the diagnosis tool to see if we did a good job. That's the PK part. Then you say, okay, now my model includes also a PD part, pharmacodynamic part. And now you have to take the model that you already developed and add on top of that the PD component. This is called PKPD analysis. Then you are going to tell the program, in this example, it's a simple example when the pharmacodynamics is defined by an indirect response model. And then now, what's the model building? You need to find initial estimate. You need to check the initial estimate. Do we have good initial estimate? And you have a special tool that allows you to do that. Then you run the model and you say, okay, now I found my parameter. I want to know that if I would be able to simulate data with the final parameter and with the exactly same design than the one that I start with, am I going to get similar results than the one that I start with my observation? Suppose that you did a good job, then you are going to see that there is a match. And you have all the tools that are available here within the Phoenix environment. Everything is done automatically, and you can have a good sense about how good you were. Finally, you say, okay, now I want to have nice plots. I want to create tables with prediction at many times. Not only the observation time, but I want to have a smooth curve. I want on top of that to show for each patient the full prediction, a smooth prediction, and at the same plot, I want my observation. Then for each patient, I want to see how well I did. Then we have three features, main feature in the Phoenix NLME program, which first, you have a lot of models that are built in, like you have in non-MEM. The second feature, which is unique to NLME, is the ability to define new models through a graphical interface. And it's something that is very, very useful. I'm going to show you at the end how you can do that. You can define compartments like absorption, central, peripheral, elimination compartment. You can create flows. My drug is going from one compartment to another compartment. The flow can be linear or nonlinear. You can also create as much as you want observation, like pharmacokinetic, pharmacodynamic, or clinical endpoints. And at the end, if you are familiar with the control stream like you have in non-MEM, you can do exactly the same thing with an NLME. It's called the edit as textual mode. And I'm going to show you something that is very unique to an NLME, is that whatever you do in either the built-in mode or the graphical mode, automatically you get a translation into a control stream, edit as textual code. And that's really a very, very unique feature that allows you to really learn very easily how to code in an NLME. You almost never need to learn anything by heart. Then, as I mentioned, when you really have data, nonlinear mixed effect modeling is the tool that we are using to find the parameter. But most of the time, we don't have the data ready. Then we need to use some manipulation. And Phoenix NLME has unique tools that allow you to do that. In the pharmacometrics, my hope is that more and more people from different disciplines will enter into that field, and not only the geeks in mathematics and statistics, but I believe strongly that many, many people have incredible skills in different disciplines like clinical pharmacology or even medicine, and they should enter into that field because it can be very useful. The problem is that up to now, all the current software are not easy to digest for people that do not have this natural ability to enter into really complex world of the modeling and simulation. But they really understand the processes. And what we designed in all this interface and all this program is you the ability, if you are novice, if you are interested in clinical pharmacology, you can get in. If you are interested in pure mathematics, you can get in. Pure statistics, you can get in. Then this kind of software will give the ability to people from different disciplines to interact and to be able to use the program optimally. We have different kind of engine optimization because you try to find parameters. And you have a graphical interface, and as I mentioned, you have three kinds of features that you can use: built-in models, graphical, and textual. It is very user-friendly, and I really strongly believe that we do not lose flexibility, because most of the time you add user-friendliness and then you lose flexibility. Here, we have a very nice balance between to still be user-friendly, but still give you full capability. Something unique to NLME is that if you put units in your data set, the program is going to compute the output units. Then it's doing, basically, it's taking the model and compute the units, use the input units, and give you output units. And all this I already explained. I would like to go now as far as possible to the demonstration. And then what are we talking about here? It's a PKPD model, and the following slides had the demonstration, but I'm going physically to show you basically what has been done using the software. The first thing to do is, of course, to open the software, and then the steps will be first you need to import the data. The data are coming from a non-mem data set. Then we need to manipulate the data to transform the non-mem data set into an NLME data set. I'm going to show you how we can do that. And then we have to do non-composite analysis and then start in the model building. Then let me show you basically the different steps here. Then if you open the software, you can click on File and you can create a new project. And then you're going to create a new project just to show you that I'm not going to win this project. You can left click and you can put basically any name that you want. For example, test. I already did that, and I called this project Webinar November 14, 2013. And you can see here that we have different, let me close. If you want to close the project, you can close. I don't want to save. And then now I have the project that I want. And the first step, you have this plus and minus, then it expands, or basically, if it's too cumbersome, then you can make it basically that way, then you see less. The first thing to do, again, the model building. I want to import the data. And you click on data, you right-click on data, and you have the import. When you import, you can select the data set. For example, here, non-mem-like data set. And then you click here. If you don't have units, there's nothing to do. You just right-click, and you basically create the data set. You can see I already did it. That's why you get a new name with in this 2. And let's look 1 second at the data set itself. It is a non-mem data set. You click a plus, and you click on sheet 1, and you can see that in the non-mem data set you have EVID, you have CMT. EVID 1 means that you have a dose, and you have CMT 1 for PK and 2 for PD. Then the response are all stacked into the same column, which is the column DV. And NLME doesn't support the stacking option, but require you for each response to be defined in a different column. You can say, oh, yes, that's a problem for me. I don't know how to do that. And that's why we add all this a very useful tool that allow you to manipulate data. If you want to do something with a data set, you just take your data set, and I'm going to show you the result. I'm just going to show the strategy. You right-click, you put Send To, and you go to Data, and then you can append a worksheet, the important one, append worksheet, merge worksheet, split worksheet, stack worksheet, etc. Then what do we need to do? In that case, you can see I start with a split worksheet. You click on Setup, where you decide what you are going to do. And then, what is the decision? I want to split my data set by CMT and by EVID. And you click CMT, EVID. You click on Run or F7, you see it here. Every time you want to do something, you can see Execute Split Worksheet. And that's the results. And you see the results are here. Then, for example, 1, 0, it's CMT equal 1, and then EVID equal 0. It will give you basically all the PK data. This will give you all the dosing data, the dose. You can see A1 is the dose. And this will give you all the PD data. Then the next step, you cannot edit that. You cannot change nothing if it's just an output. But you can take this data set and click on Send To, and copy to data folder. If you do that, you are going to get the result of the split worksheet in your data. And you can see it's here. Now what I did, if I'm taking 1, 0, now you can edit the name. It was DV here, and I changed the name instead of DV. I want to reflect that what I have is the PK data. And then I put the name COPS to define my PK response. And here, these are my dosing data. I just can leave it the way it is. And that's my PD data. It was DV, and I changed DV into EOPS, which is my PD data. The next step, now that I defined for PK and PD a different name, I can just append the 3 worksheets: the dosing worksheet, the PK data, and the PD data. And because I defined a different name for PK and PD, they will show up in a different column. This is the append worksheet. In the setup, you tell him, I want 3 worksheets, and then you define what you want in each worksheet. This is the PK data. Then what I want is the ID, the patient, time, the observation, and the dosing. These are the dosing data. I just want the ID, time, the dosing, because I just put the dosing information, and every time that I'm giving a dose, that's basically the AMT in non-lab. And here I'm just telling I want ID, time, the PD, because there's a PD data, and the dosing. And you click on execute or F7, and then you get the results, and that's your PD data, and that's your final data set. What you did by using just split and append worksheet, you create your data set that now can be used for NLME purpose. Now, let's just start now the model building. And again, this is very important. In the model building, you always start with a non-comparison analysis if you are talking about PK data. And what you see, what you basically did, you take your final data set, and for example, here I take result from append worksheet, which is the append worksheet that I put in the data by using send to and copy to data folder. You go here, and every time that you want to do something, you right-click, you put send to. And here, for example, you put NCA and NCA. This creates an NCA object, which is that one. Okay? You can go click on setup, and this is the name of my data set after basically the manipulation. I call it sim PKPD for fit. I'm sorry about the telephone. It's a home and with 5 different phones. Hopefully it will stop. Then you have sim PKPD for fit. That's my data set. And in the setup, I just want to see, okay, that's my main. I want to sort by ID. For each patient, I want to get the non-comparative analysis output. The time is the time. And the concentration is my data that I have for PK, because I'm starting with non-comparative analysis on the PK data. Then I click on dosing, and basically to put the same data set into the dosing map, it's very easy. You just take the data, you just click on NCA, and you take the data set and you just grab it into the mapping area. And that's very easy. Same thing for the main and dosing. Now you need to give the dose information. You sort by ID. The time of dose, it's the time column. And then A1 is the amount in the first compartment at equals 0. Whenever you give the dose, then that's basically map with the dose. Then you click on execute, F7. You can see that it's every time you are doing the same thing. And then you get results. Now, if you look at the results, you are going to see all the final parameters. And what is unique to the NLME environment, the Phoenix environment, is that any output can be used as input for the next operation, for the next things that I want to do. Then I can right-click, I can send to, and I can, for example, do descriptive statistics. Why I want to do descriptive statistics? Because I want to know the average for using all the patients for both the clearance and the volume. Then you can see here, I have a descriptive statistic object. And I just ask him, I want the VZ and the CL, okay? If it's observed or predicted, it doesn't matter because I just need an initial estimate from my population. Then I decide I want to get information about the volume, the clearance. You click on F7 or on this tab, and you look at the results and say, okay, very good. My clearance, a good initial estimate for clearance will be 5. A good initial estimate for volume will be 50. And now I remember that I put this somewhere in the sheet, and I say, okay, now I'm going to start my population analysis. Strategy, I want to start with the one compartment model. I'm doing that. I'm taking my data set, for example, this one, and then I right-click, send to Phoenix model, Phoenix modeling, Phoenix model. And this you can, because I create different like folder, and you can decide whatever folder you want, where you want this object to be created. And you can see here, create it here. Okay, but I already did the job for you then, and you can left click and you can change the name. This has been called model PK1C. Then the input, it's my sim PKPD for fit, and that's my data set. And now you have to answer different questions. I'm starting with the PK analysis. You have a different type of model using what is called the building feature. That's if you know it's a well-known model, 1 compartment, 2 compartments, 3 compartments, linear, non-linear, then you can use that. You can see that you have different options, PK, Emax, PK, Emax, PK indirect, linear, and PK linear. But it's a PK model. Then the first step is to decide the kind of parameterization. I'm going to use micro-constant or clearance-based parameter. And I suggest you to use always the clearance-based parameterization. It's more robust and it's more physiological. But you have the option, you can micro-constant or macro-constant. Pay attention also that whatever you do, you can always look what's the translation into the NLME code, what is called the PML, Phoenix Modeling Language. You click on Model Text, and you can see here the current translation of whatever you make, whatever you decide. If I'm going to change something, automatically you will have a translation. When before it's closed form, which means there's an analytical solution for the model that I'm talking about. If you don't want to use a closed form, you uncheck that, and you see on the right a snapshot of the differential equation that define your model. If you want to see completely what you have, you can see it here. What goes out, it's 1 compartment model, it's just clearance multiplied by C. I want to use a closed form. Then the next step, I define the model. I want to define the error model. We have different default error model, but if you want to write your own error model, you have also the option if you use the control string mode or what is called the edit as textual mode. Multiplicative means proportional or constant CV. I don't know exactly what you are familiar with. That's the traditional one that when you see that when my concentration is large, then I have a lot of error. But you can choose additive, log additive. I would suggest you to use always as first in your first analysis multiplicative for PK. And for PD, it's less drastic, it's less important. You can only use multiplicative, but many use also additive because the PD data spend over a small range than the PK data. The 0.1 here means 10% CV. When you use multiplicative error, 0.1 is basically the CV. Okay, 0.1 means 10%, which is usually a good initial estimate. Don't ever put 1 or 10 because then what will happen is your optimizer will have some problems because you suddenly put too much error and it will be a little bit in trouble. Okay, then I define the model. I define the what is called the structural model. I define the error model. Then now I need to define what are the initial estimates I want to put for my volume and clearance. It's an IV mode, and I have any clearance and volume. You click on parameter and you click on fixed effect. Now remember what we did with the non-compartment analysis. We find that natural estimate of 50 for V and 5 for clearance was good. Then I'm just using what I got from non-compartment analysis. I can round because I just need to be in the bulk part. Then you need now to define what will be the variance that I'm going to put as initial estimates for volume and clearance. You can always use the default. You click on random effect. And then you have 1, 1, which means because the data in the default is to assume that the parameters are log normal distributed, like you do in non-MEM most of the time. And 1 mean 100%. It's a good idea to start with 1, 1, and the program is going to find the final estimate for the variance. If you want a full variance covariance matrix, you uncheck that, and the program is going to find also the covariance and the correlation that I want to do here. Then I define the fixed effect, the initial estimate for the mean value if you want, the random effect. And then finally what I need to do, I need also to define the kind of optimizer, of engine I'm going to use. The default, I suggest you to always start with FOC ELS. Once you are going to get the new version next year, then there's a new algorithm called QRPEM. I've been involved in the development, and also I was the co-developer of the algorithm implementation with Bob Barrer into different software, as you may recall. Then you define the engine that you want to use, and finally you need to do the mapping. You have to be extremely careful with the mapping. If you see no warning, it's a good sign. Then you click here in Setup and Main, and all my data have both my data set has both the dosing information and also the information about my PK data. Then I just can use it, and I can map ID with ID, the patient, time with time, the PK observation in my data set with basically the observed response in my model, that's COBS. And then I have to tell him, okay, in my data set, A1 has the information about my dosing. You can see A1 is here. I give a dose of 10. And then I have to map this with also A1. If the names are the same, it will automatically be mapped. And then the next step is say, okay, if I'm not sure that I start with good initial estimate, you can click on initial estimate here. And when you click on initial estimate here, take some time because I'm running a heavy data set somewhere in the background here, downstairs. Then you can see here that you can see with this initial estimate what's happening. You can click here, same axis, which is not a good idea. You can split. You can have more patients here or less. You can look everything in the log domain, etc. You can overlay all the data in the log domain or not in the log domain, but here it's not really useful. Then you can see when I'm going from one patient to another patient, apparently everything looks fine. In other words, these are the observations, and that's the average prediction. Okay? As long as you see that your average prediction and observation are in the same kind of, basically spend the same kind of Y value, then you know that you have a good initial estimate. But you can change that. You can here put, for example, 50 interactively. You are going to see the change. You can put 100, and you can see that once you do that, it starts to be really off. Then you can put again, for example, 50. Okay? And here, if I'm putting 5 as initial estimate, see that it looks good. If I would put 4, for example, and I would be happy with 4, you can see here that is a black. The color is black, and you can touch here, you can click here, and then you copy this in your initial estimate. And if you don't do that, the program still is going to use what you saw here in the fixed effect. Now, when you put 4, you keep 50, and then you have 4. If you change your mind and put 5, then you can put 5, and that's what will be used. The next step is to run the program. You just click F7, or you click on this button, and then you're going to get the results. Now, once you have the result, you can say, okay, I want to see if I did a good job. And the most important one is plots that you should look at. It's, for example, what is called the conditional weighted residual versus time. You do that. I mean, and it looks not bad at all, okay, which I'm happy, but I want to make sure that basically the data are good. You can see the DV versus IPRED. It is you observe versus individual prediction, and you can have also the observed versus population average prediction. It looks quite good, and I'm happy, okay? Then everything looks good, but I'm not sure that it is the best model. Then I want to go to the next step. You can take your model, and you click on copy. Then you click on the model building here, and you put paste. When you do that, then what will happen, you will have a copy of your model here. Now you want to tell, okay, I first want to accept all the final estimate that I got from my previous run, which was the one compartment model. In order to do that, you click on parameters, you click on fixed effect, and you see, and you click on accept all fixed and random. Now, these are the final value that I got from one compartment. But now I want to shift to the 2 compartment model. You click on structure, and instead of 1, you just put 2. Now, because I put 2, I have some additional parameters that have been added, and I will need to initialize them to put an initial value. Now you click on parameter and fixed effect, and you can see that V2 and CL2 has been added. Okay, you want some tricks? I will give you some tricks. If you want a good initial estimate for V2, just put roughly what you got for V, which was 50. You don't need to put 51.639, okay? And here it was around 5, and you put 5. And say, okay, that's the only thing that you need to do. For the random effect, you want to keep what you got for the V and CL and just put 1 the default, okay? And you can click again on initial estimate to make sure that what you get still makes sense. And I say in the same, nothing really happened, then everything is good. And you can run that model. And you can, again, look at the results, which is that one. I already did it before, okay? Model PK in 2 compartments. And you can look at the results, and you are not going to see a lot of difference because it was already good before. You can see that I'm getting the same thing. They say, okay, the 1 compartment is good, the 2 compartment is good, but what is better statistically? Then that's where you go with what is called the model compare. How you do that? You click here, New Phoenix Modeling, and you click on Model Compare. When you click on Model Compare, the Model Compare shows up. You click on Setup, and you can tell him, okay, these are the model I want to compare, 1C with 2C. Please keep the order, that the 1C is the small one and 2C it is the bigger one. If not, you have to swap, and you can do that, but try to do it logically. Then you start with a small number of compartments and then large number of compartments. You just check, and then you click Execute. Now you understand the business, and you are going to get the results. The result will give you a p-value. But you can see the p-value is that when I shift from 1 compartment to 2 compartments, what is the p-value? But what do I mean a p-value? The assumption is that the 1 compartment is called, basically, it is defined as the null hypothesis. And you see, okay, if my model was a 1 compartment model, and I would run a 2 compartment model, what is basically the probability that I should, basically the probability to get the result that I got with the 2 compartment model, when in fact the wheel model is the 1 compartment model. The bottom line, if you get a very small p-value, it means that I got a really difference in the optimization procedure when I use the 2 compartment model, and the probability that really my true model is the 1 compartment is very small, which means that I would opt for the 2 compartment model. When you get a very large p-value, here is 1 because there was no difference in the likelihood, it means that you should stick with the 1 compartment model. Okay, I want to now to stick with the 1 compartment model. Then what's my next step? My next step is that I don't care about the 2C. I'm taking this compartment, this model, white, click on copy, go here and click on paste, and now I change the name to 1C because now I want to add the PD component. How I'm doing that? Remember, the first thing to do is first click on parameter and fix effect and accept all fixed and random, which is the 51, and I already did it for you. Now, instead of the PK model, that's what we select before, we are going to select PK indirect. Now, PK indirect model, keep the same model for the PK, and it has already the final estimate, but it's adding an indirect response model. The indirect response model tells you something like that. I had my PD data that were at steady state when I start, my trial, and now I'm adding a dose, I'm adding the drug. And because of the drug, the production of my biomarker, which is my PD response, increase as a function of the concentration of my drug. It's called stimulate limited. And you can say, okay, I don't understand what I mean stimulate limited. You just can click on model text, and you can just look here what is called the differential equation. Derive E means d dt. The change in the response with time is equal to the production of my biomarker that is stimulated by an Emax model. Emax is the maximum stimulation that I can have, and it's dependent concentration. It's an Emax model that you put on that. Okay? At the same time, my biomarker is eliminated via what is called the first order process minus k odds multiplied by E. Okay? And you can see that the program has been, you have the translation into code that you can use later if you want, but all this has been done for you. Okay, then everything is good. And now I need to define again, same strategy. I need to define my error model for PK, which I already did. And I want to use, in this case, also multiplicative for my PD, and 0.1 means 10%. And the next step is to go to parameter, fix effect, and I need to put some initial estimate. Now, I don't have time to explain you how to find good initial estimate, but it's not difficult. You look at t equals 0, and k in divided by k out, it's basically my baseline for my PD. And if you look at that, at data, you're going to see that they all start around 100. And I know that the ratio should be 100, then 101 is a good value I can start with. I can play. At least the ratio will be 100. Now, the Emax, you can look now at the, you have 3 doses in this data set. Just look at the high dose, and just look in average what's the maximum increase that I have compared to baseline. It gives you, and you're going to see that it starts around 100, and some patients go to 1,000, then from 100 to 1,000, it's a factor of 10. Then I just need an initial estimate, then this is a good value. EC50, here's the trick. Look at all your data, and just look what is roughly the average concentration that you have, because EC50 is concentration. You're going to do that, you're going to see that 10 roughly is something, it's a good average that I could use, and just put that. The idea beyond defining EC50 as the average is linked to the fact that if my real EC50 is completely out of my observation data, I will never be able to estimate it. Then assuming that I can estimate it, I should use something that it is in the bulk concentration, and 10 is a good method. Then again, you can click now an initial estimate, and now you're going to get both the PK data and the PD data. It allows me to do that. Then you can see here E versus time. You can either C versus time or E versus time. And you can see here E versus time, my initial estimate looks quite good, the average. And I can see the prediction. I can see, again, it's an average. Then, of course, it will not match. Then I can see that where my observation, my prediction is roughly at the same spot, then I feel good. You can click on the run, and you're going to get the results. And click on results after you run the model. And now you can, again, the most important one to look at is the conditional residual. But now you're going to get conditional residual for both response. I know that the PK was already good, but be careful, because sometimes if you have bad PD data, it can contaminate the PK data, and that's why you should do it sequentially. First do the PK and the PD. I don't have time to explain you that, but it's a feature that in the new version will allow you to do that using the interface, something very nice. And I can see here that it looks very good. The blue should be around 0, and just to let you know, the red should be around 0.8. That's a trick. If the red is around 0.8, it means that it did a good job. You should see constant variance. In other words, you should see that what you have, all the data that you see in the conditional results should be between -2 and 2 for at least 95% of the data, and it looks good. Then I'm happy. And now I say, okay, that it looks good. Now the next question is, if I would simulate data using the same design, same time point, same dosing, etc., using the final estimate that I got from my PKPD model, would I get similar data than the one that I observed first? And this can be done by copy that model, copy and paste, and shift and accept all fixed and random. I click parameter, fixed effect, and then you accept fixed and random. I already did it for you. But now you change the run option, and instead of using the simple mode, which is a fit, you click on simulated predictive checked, and you add 0 iteration. And what the program is going to do is going to take all your data, and because I have a lot of data, you can ask just to do 1 replicate. In other words, to simulate output for PK and PD using the final estimate, but just do it for the current individual, because I had already 300 individuals, it's enough. If you want more, you can click on more replicate if it's not nice. And what the program is going to create for you, it's called confidence bounds. What you should see in the confidence bound, you should see that for each dose, and I'm going to show you the result in 1 second, I can see that my observed data are 95% of my observed data are within what 90%, within what is called the 90% confidence bound for my PK and PD. Then the only thing that you did, again, you accept fixed and random, you have 0 iteration, 1, you can see 1 replicate, but that, I put also stratification. I define dosing as a covariate, and you can see, you can ask me by email how we do all that. I don't have time to explain everything. Then the program is going to show you as output here somewhere. I run that program. And you see here that one of the options is the predictive checks. And you click on here, and here is what you are going to get here. Because I stratify by dosing, I'm getting my observation, and here the black curves are the predicted quantiles. You can see the predicted, it is the 5%, and this is the 95%, and this is 5%, and this is the 50%. And you can see that the black confidence bounds englobe roughly 90% of your data. And you can see this for both the PK and the PD. Okay, that's PK, PD, PK, and PD. Then now I feel really good that I believe that if I would simulate data, response data using the same design, the final estimate that I got for PK and for my model, for my PKPD model, I would get similar data than the one that I start with. And that's something that's very important. And again, it has been automatically done by the program. Then last, before we shift to the graphical option to show you that you can do everything with the graphical option, I want to copy my final model, this one, copy and paste, copy and paste like we did before. Right-click copy, you click here and paste. And now what I want to do, I just want to create tables, okay? And in other words, I'm just going to ask for one iteration because I already say parameters, fixed effect, accept all fixed and random. Then I'm already there, then I don't need a lot of iteration. That's why I'm going to run option, and I can even put 0 iteration. But now I still keep the simple mode, and I click on Add Table. STQ means sequence, and I want the program to simulate for me, for each patient, from time 0 to 10 by interval of 0.1 to simulate the predicted concentration, to simulate it, the predicted response for PD. When I have in my data set an observation, I want the program to give me that. It's called C-ops and E-ops. When there's a dose, I want the program to give me that. The name of the dose is A1. And also to give me the information about the dosing because dosing has been defined as a covariate. When you do that, you click on execute, and you are going to get a table. It's called table 1. You see table 1 here. And now what you have here is for each patient, you go from 0 to 10 by interval of 0.1, as you can see. When I have a dose, it's written here in that dose column. When I have an observation for PK, you can see it. When I have an observation for PD, you can see it here. And now you have the smooth prediction by interval of 0.1. You can see it for seeing this. Then you can right-click here, send to plotting, and do a plot. Now, I did the plot. You can see that now I can see for each individual, I have the observation, PD, for example. I just asked for the PD. I could ask for the PK. And now I have the smooth in blue, and I have the data. And this gives you another kind of confidence that for each individual, it's well represented. That was the built-in feature. And now finally, for the next 5 minutes, I'm just going to show you that you can increase flexibility by basically taking the data set, my original data set, which is this one. You can create a model, send to Phoenix modeling, Phoenix model, and let's say graphical model, and you say select. And then you click on edit as graphical, and you say yes, and you say yes. Now you can start to edit that. You go here, and you can do a lot of stuff. You can right-click any empty space into the graphical area, and you put insert. You can add a compartment, absorption compartment. And you can move that one here. It means that I give a dose here. But now you need to tell the program, I want to put a dose, but I want the dose to go to my central compartment. You click any empty space, insert flow. Then the program asks, select first compartment of flow. You click here. Select second compartment of flow. You click here. And now key Ka has been defined. But you can change K into a clearance, which doesn't make any sense. But you can also have like a saturation, like when you have a patch that you put on your skin. and you have variability issue, and you know, the KA, it's not really linear or whatever, then you can make whatever decision you want. Here, it's KA. Now you say, okay, no, I did a mistake. Click here, and you can delete, and say delete. Then now it's not there anymore. You can also add, insert, and you add a peripheral compartment. Let's say you want to shift from one compartment to two compartments. Put here. But now you have to tell him that I have a flow between this, and that it's bidirectional. Put insert, flow, from here to here. The default is bidirectional, and the name is default here, but you can change the name. And again, here, you have different kind of parameterization. Don't want that? Put delete. Say that. Okay. Now, this is the green box. It's an observation. And you click here on the observation, and you see the name of your variable, of your observation, COPS. The input, which means that corresponding prediction is C, and you can see that they've been connected. Okay, that's the default. Then now this is the error model, and you can change that. You can put multiplicative, and then you can put 0.1. Every time that you made a change, you can click at model text, and you are going to see the translation here. That's the code for multiplicative, but you don't need to know that. Okay, at this point. Then you do that. But in fact, here, if I click here, you see micro, but I want the clearance. And I click on micro, and I put clearance. And now I'm in the clearance parameterization mode. But I had a PD model, and my PD model was an indirect response model. How can I do that with the graphical mode? Very easy. You right-click any empty space in the graphical area, insert, PD, and indirect response model. You can take this, you can make it bigger, and this is, you can see the input C. Now you have to tell the program that this C and this C are the same. You take the cursor here until you see the small circle, you left click, and you connect. Okay? And that's the connection. And you move all this stuff in Archie. You can see that. And now you connect. You connect basically the PK with the PD, and you say that the input in the PD model, it is the concentration of PK. Again, you can click at model text. And now you're going to see the differential equation. That's for the PK, and that's downstairs. Now if you go down, you can see that's the model for the PD. Now, I had also observation for the PD. But I don't see a green, I see a green box only for the PK. And I can right-click, insert, observation. It's a continuous response. And now you can see that I have a new observation. Now, you can never use the same name twice. Then you can click on this box, and instead of C, you put an E, which is good. The input should be E, which is the predicted response. And here you can never have the same name even for the residual error model. Then you put an E here. I want proportional, and you put 0.1. You can see full flexibility. Now you have to tell him, this is my indirect response model. You can see here, this is E, and this is E. But the program doesn't know that. Then you need to connect them. And you go here, and you connect them. And now basically, you define the same model that I used, that I showed you 10 minutes ago, but now it's in the graphical mode. But you have now full flexibility. Click on parameters, fix effect, and now you can put the value, 55, 10, 10, 101. You change the value, and then basically, for example, I put 50, then 5, 10, 10, 101. I can click on the, again, initial estimate, and hopefully it will work, but that's not the point. Then this finish the demonstration, and I will be happy for the 10 minutes that are left if you want to ask some questions. Of course, this is just a demonstration. I strongly suggest you to go. I'm giving, and other trainers are giving often in both USA and Europe 3 days introduction to population PKPD. I'm giving also advanced course, but this will be done only when we are going to give you the new release. And thank you very much, and I'm waiting for questions if you have some.
Okay. So the first question came in. What MS acquisition software does Phoenix NLME work with?
I don't understand exactly the question. I mean, you can link the Phoenix NLME with other software like non-mem, S+, R, because there's what's called Phoenix Connect, but I didn't talk about that here. Then I would need more precision about what exactly do you mean. You cannot directly connect. You can run Phoenix. You can run other software within the Phoenix environment, like non-mem, R, and S+. But if that's the question, then that's the answer. But maybe the question is a bit different.
Serge, in your experience, how long does it take someone who has never done nonlinear mixed effects modeling to learn the Phoenix NLME program compared to non-mem?
Okay, I will tell you the truth. When I'm giving a course of 3 days for somebody that was not exposed at all with the Phoenix environment, but have some background in population PK, then under the assumption that you know what is pharmacometrics, after 3 days, they are ready, basically. And I think that this is a big difference compared to the other software that would really require more time. And what's happening is that first the training, you get really a full course that basically you can keep at home. And the user interface is so easy to use that after 3 days, I believe that you can really start be quite independent. At the same time, if you have any trouble, you still have the forum that can be used, and people can also contact trainers whenever they need. Then I believe that after 3 days, I cannot answer really about non-mem and other software, but I strongly believe that it takes really more time because the basic non-mem software doesn't provide you all this model building, interface-based strategy that are built in as a part of the software itself.
This will be the last question that we have time for. Can you talk a little bit about how you can use Phoenix NLME to uncover covariates such as gender or age, or how that might affect your PD response?
Oh, and that's very easy. I didn't do it in this example, but the way to do it, you just take your model. Let's say the one that has the create table because I had a covariate. Okay. You see, for example, here the dosing. That's the only covariate that I define. The way to do it, you click on structure here. You click on parameters. And you click on structural. Parameter structure, and you can put add from unused. Now, the truth is that when you click on add of unused here, dosing has already been added, then I don't need to do it. But I can show you how you would do it. I can uncheck there, for example. Let me show you, for example, how you would do it. You click on parameter structural, and you click on add from unused, and now you're going to see the dosing showing up. You can see dosing and add. And now the dosing has been added. And you click now on covariate type, and the default is that dosing is continuous. But if dosing was not continuous, you could click on categorical. And for example, you put any name that you want, and I think that the dose is 10, 100, and 1,000. Then you put 10, you put 100 with 100, and add, you put 1,000. Again, on the left, you can put whatever name that you want. Now, what's happening is now you create category 10, 100, and 1,000 for the covariate. And suppose that you want to say that the clearance depends on the dosing. And maybe the volume depends on the dosing. Just click here and click here. And you can see that automatically the program, if you look at the model text, creates what is called a covariate relationship. It's telling me that my volume depends on the base volume, multiplied by exponent, a coefficient, multiplied by, and then dosing equal means that this term equal 1 if in your data set the dosing is 100, either it's 0. Then you create an additional parameter here and an additional parameter here. You have 3 dosing, then you have 2 degree of freedom, and then you have 2 parameters. And then the automatically default is that these parameters are initialized to 0. And 0 means that basically there's no covariate relationship. Now you run that model, and if you run that model, you are going now to get parameters, estimates for this covariate-based relationship parameter. And that's the way to do it. And now the covariate type can be either continuous, which is the default, or categorical, or you can have also inter-occasion, which means, for example, you have crossover studies, and you believe that maybe from occasion to occasion, something can happen because I change the treatment, and I can have a treatment effect. Okay?
Okay. Thanks, Serge. A reminder that a link to a replay of this webinar will be available on the Certara website within the next few days. On behalf of Certara, I'd like to thank Dr. Guzzi for this presentation, and I would like to thank you all for attending today. This concludes today's webinar, and you may now disconnect.
Okay. Thank you. I guess I can disconnect also.